Hello everybody, it's Spider Pilot 747 here, and today we're talking about the Otto cycle, which is a thermodynamic cycle consisting of, an isentropic compression followed by a constant volume process here, which we can call P. It's a constant volume heat addition, so we'll have a heat input, followed by an isentropic expansion, followed by a heat output. Now, this is a representation of the type of cycle you would see in a gas engine. So you would have, for example, in an actual gas engine, you would have, let me represent that in blue here. In an actual gas engine, you would have an intake followed by your compression, which might not be actually isentropic, followed by an I should maybe make this an almost constant volume heat addition, which is the burning of the fuel. You don't quite get to that point up there, and then you have, again, an almost isentropic expansion, and your, finally, exhaust here, slightly higher pressure there, and then it goes back around. So, essentially, the Otto cycle is going to give you results that should be similar to the actual cycle. Now, some notable differences that you will have, for example, this heat addition is not instantaneous, so you have timing losses resulting from the fact that it takes a finite amount of time for the fuel to actually burn. You're going to have losses due to the isentropic compression processes and expansion processes because they're not truly isentropic. You have some heat transfer out of the system there. And you're going to have a little bit of pumping losses here resulting from the fact that you actually have to pump the fuel and air mixture into the cylinder before you burn or even compress. So what we're going to look at today is getting some of the basic values that you're going to want out of this, such as, for example, the net work and the thermal efficiency of the cycle. So we're going to start by specifying what our system is going to be based on. We're going to have a full octane fuel C8H18 with a heating value of 44,427 kilojoules per kilogram. The air-fuel ratio is pretty close to stoichiometric. We're at 15. Now our air in this example is going to be calorically perfect, which means that we have a constant specific heat ratio of 1.4. We have a constant pressure specific heat capacity of 1.005 kilojoules per kilogram Kelvin, and a constant volume specific heat capacity of 0.718 kilojoules per kilogram Kelvin. Now our engine, these two volumes here, we have volume 2 being 1/8 of volume 1. So in other words, we can say that our compression ratio is 8, because our volume after compression is 1/8 of the initial volume of the cylinder. At intake, in other words, point 1, on the diagram up here, we have a pressure of 101 kilopascals and a temperature of 298 Kelvin, which is pretty close to what you would expect in a standard atmosphere, almost. So, first what we're going to do is we're going to find the values around this diagram. We're going to start at 1, we know what's there. We're going to move on to 2, we're going to figure out what the temperature and pressure is there, temperature and pressure at 3, and then temperature and pressure at 4. And that will help us to get all of the values that we need to know for this engine. So, moving on to point 2, so isentropic process from 1 to 2. So we're going to find what our pressure and temperatures are at point 2. What we know is this volume ratio, so V1, or we should say V2 over V1 equals 1/8, since V2 is 1/8 of V1. So we know what this volume ratio is. Now, based on the isentropic compression equations, we know that P1 over P2 equals V2 over V1. These would be specific volumes, which is 1 over density, and this would be raised to the power of gamma. So we can find what our pressure at 2 is. a little bit of rearranging, we'll find that P2 equals P1 times V1 over V2 to the gamma. And that's just rearranging this equation, bringing P2 over this side and dividing by this, and we get the 1 over that. And what we will find equals 101 kilopascals times, we had a compression ratio of 8, so V1 is 8 times V2, to the power of 1.4 for our calorically perfect gas. And the pressure we get is 1856.3 kilopascals. And that's what the ideal pressure is after this compression. Again, you could have some pressure losses, and we could have a process which is not truly isentropic, so there could be some losses in addition to that. Finally, we have our temperature, T2. The isentropic relation for temperature is going to be T1 over T2 equals V2 over V1 to the gamma minus 1. So in other words, our temperature T2, similarly, is going to be equal to T1 V1 over V2 to the gamma minus 1, which we will find is 684.5 Kelvin. Now, one important thing to note, we've just increased our temperature by more than 400 degrees. Well, by approximately 4. We've just increased our temperature by a little less than 400 degrees. Now, in a real gas, our specific heat ratio is not constant. And in addition to that, our values for Cp and Cv are varying. And that's varying with respect to temperature. However, we do not exactly have a formula which is going to be representative of this, or at least it would not be easy for us to have a formula. So for this simple example, we are going to be ignoring that, and we're saying that we have a calorically perfect gas where these are all constants. However, it should be noted that in reality, they do vary. Another way of solving this problem, if you wanted to account for that, is instead of using this isentropic compression process, you can use tables which give the ideal gas properties of air and basically alter the specific volume with your compression ratio. So next we're going to do our heat addition. So we've got these two values up here. I'll underline them in blue. We got this one, we've got this one. Now for point 3, or in other words, the process from 2 to point 3, which is our constant volume heat addition. Now, this is where our fuel properties come into play. We know that our heating value here was 44,427 kilojoules per kilogram. Now, this is important to note of fuel. That's per kilogram of fuel. Now, we have an air-fuel ratio of 15. So with this air-fuel ratio of 15, this means that mass of air over the mass of fuel equals 1/5. So if we want to convert this heating value into something equivalent for our actual system that we have here, what we need to do is we take our heating value, which is Q per m fuel, make that a lowercase q, our heat input per mass of fuel, multiply that by the mass of fuel per mass of air. These two fuels cancel out and we get Q over m air. And that's what we want for our equation, our basically heat addition per kilogram of fuel. Actually, now that I think about this, that should be a capital Q. And now it's completely legible. Let me make that a capital. And that's compatible with the system that we've already specified. We're doing this all in terms of air. So with an air-fuel ratio of 15, we can basically take our heating value and divide that by our air-fuel ratio which is 44,427 kilojoules per kilogram of fuel, divided by 15 kilograms air per kilogram fuel, and we get 2961.8 kilojoules per kilogram of air. And since our whole system is in terms of air, this is the value that we are using for that constant volume heat addition. So let's plug that in. We have Q in equals M air CV, because this is a constant volume heat addition, and we have delta T from 2 to 3. So constant volume heat addition, this is our equation. We don't know what the mass of air is, we're leaving that variable, so we'll have lowercase q in, which is capital Q in over the mass of the air, equals CV T 2 to 3, delta T. And since we know this Q in, 2961.8 kilojoules per kilogram equals 0.718 kilojoules per kilogram Kelvin multiplied by our delta T. We'll just leave that as delta T for now. We divide this over to here, and we find delta T from 2 to 3 equals 4125.07 Kelvin. So that's how much heat is that's how much temperature change we get from our heat addition into the system. And we're not considering the heat capacity of the fuel and the combustion products in addition to this. So we will have some additional changes associated with that. We're going to have different species. We have a chemical reaction going on. We have different species after that chemical reaction. We have some chemical reactions going on which will actually take heat in. So this temperature is likely to change. And in addition to that, I'm going to put this as an important side note. We assumed calorically perfect. However, that is not the case in reality. In reality, we have a variable specific heat capacity. So in reality, this temperature change would be a lot less. So we would have a T3 approximately 3500 Kelvin under this situation. So let's calculate the ideal T3. T3 equals T2 plus delta T from 2 to 3, which basically is going to be equal to 4809.57 Kelvin. That's very, very high. And as I mentioned, in reality, we usually get closer to 3500 Kelvin. But in this case, we're using ideal gases. We have calorically perfect air. This is what we're going to get. Now, to calculate what the pressure change is, we need to say it's an ideal gas as well, which calorically perfect in addition to that, because we want to find what the peak pressure in the cylinder is. So peak pressure, PV equals RT, where this is our specific volume again. This V is specific volume. But for a constant volume process, your specific volume is going to remain the same, and your gas constant R is going to remain the same as well. So over this constant volume process, this is going to be constant. You have two constants. So P over T equals constant for this constant volume process. Therefore, P2 over T2 equals P3 over T3. We know what T3 is, we know what T2 is, and we know what P2 is. So we can calculate P3. P3 equals T3 over T2 P2. And so we can basically plug these in, and we find that our peak pressure at P3, 1343 kilopascals. That's pretty high. That's about 130 bar, which Obviously, you're not likely to actually get that. You're going to have a bit of pressure losses in there. Your cylinder is going to start moving down by that time, so it's not exactly constant volume, but 1343 ideally in the case that we're defining here. Next, 3 to 4, we have expansion. And once again, this is going to be isentropic, so we can use those isentropic relationships. In this case, we have V4 over V3 equals V1 over V2 equals 8. And in addition to that, this V4 over V3 equals P3 over P4 to the 1 over gamma. Or we can raise both sides to the gamma to get this. So we'll basically be able to say that P4 equals P3 V3 over V4 to the gamma. And in other words, V3 over V3, it's going to be 1/8 equals, and our pressure at 4 is 709.66 kilopascals. Compared to atmospheric, that's approximately 7 times atmospheric. So, just a point of interest, our pressure ratio is about 0.142. I'll come back to this later as to why we might want to know that. Now let's get our temperature. So, similar to before, we're going to have V4 over V3, we're going to have T3 over T4 equals V4 over V3 to the gamma minus 1. So we can calculate our T4 equals, our final temperature T4 is going to be 2093.5 Kelvin. So there's our temperature at 4. Now we know the temperatures and pressures at all the points on that Otto cycle. So we now know, I'm just going to draw this here quick. We know point 1, point 2, point 3, and point 4 on this pressure-specific volume curve. We know what Q in is. We calculated it earlier. We don't know what Q out is. Do we need it? Well, we want to find thermal efficiency and net work. That's what we're looking for. So W net and thermal efficiency, nu TH, are both unknowns. What do we know about both of these? Well, we know that this is a thermodynamic cycle. Energy is work. Energy is heat minus work, and we can call that net. Since this is a thermodynamic cycle, once we get back to 1, we've had no change in energy. This energy is 0. There's no change. It doesn't change. So what we can say is Q net equals work net. So if we can get the net heat, we can get the net work. And it's a lot easier to get the net heat because we just need to figure out what's going on right here. We already know what's going on here versus integrating under this and integrating under this. It's a lot easier than integrating these. So we can find Q from 4 to 1. So Q out equals mass of the air, CV, times delta T from 4 to 1. We know what 4 is. We know that 1 is 298 Kelvin. Once again, we're going to normalize this with respect to the mass of the air. So in other words, Q out is 1289.79, I'm sorry, that's 17.17 kilojoules per kilogram of air. You don't have to write the air. It's usually, you can assume that it's air is your working fluid. But that's what our Q out is. So now we can find our net work. We can find our thermal efficiency as well. So net work is going to be Q in minus Q out equals 2961.8 kilojoules per kilogram minus 1289.17 kilojoules per kilogram. So our net work, we can say net specific work, is going to be 1672.63 kilojoules per kilogram of air. What we can basically say, what's the mass of the air being taken in by the engine, and we can find how many kilojoules of work per cycle there are. And in addition to that, if we know how fast the engine is going, how many RPMs or how many cycles per second, we could then determine the power output very easily. But we're not doing that here, we're just determining the work. I could do a video later showing how you would get the power. If anybody is interested, leave a comment. But now we know what our net work is right here. So what is our thermal efficiency? Well, for an engine, what we want is net work. And what we supply is Q in. And you can think of this as being equivalent to desired, what you want, divided by required. What you have to give up. So we have to give up this Q in, but we desire this W net. So this is essentially what our thermal efficiency is. So we can say that our net work, 1672.63 kilojoules per kilogram, divided by our Q in, 2961.8 kilojoules per kilogram, and we get a thermal efficiency of 56.5%. 56.5% for our thermal efficiency. Can we get that? Well, no, not really. The reason is, this is an ideal thermodynamic cycle. In reality, we have losses due to the fact that it takes a finite amount of time to burn the fuel. We have heat losses through these isentropic compressions, making them non-isentropic, so we have a little bit of loss there. We're going to have a non-constant volume heat rejection, because in other words, when we are exhausting, it's not going to be constant volume, it's going out. And in addition to that, we're going to have pumping losses because we have to pump the air into the cylinder. So in reality, our overall efficiency is going to be less. Now, back up here, we were discussing pressure ratio, 0.142. That is significant in some way, and I'm going to explain that here. Why is it important that our pressure ratio is 0.142? Well, it's important for noise concerns. You might not really understand this at first, but combustion is pretty well silent. So we don't really hear fuel burning. Much like if you were to light fuel on asphalt, you wouldn't really hear it. You just kind of hear like a whoosh, and you wouldn't hear much after that. Very similar to inside of a piston cylinder. You don't necessarily hear the combustion process happening. So when you hear the characteristic engine sound, what are you actually hearing? Well, look at this pressure ratio. And let's consider if we have a fluid at Mach 1. We have a pressure ratio of about 0.528. So for a fluid to go to Mach 1 and then supersonic, the pressure ratio has to drop to 0.528. We have a pressure ratio of 0.142, which is significantly less. So in other words, this fluid wants to go supersonic. So the shrouds at the exit are typically going to be more concave than anything, and you're going to try and get you might have expansion waves going out as well, which is going to help to suck any additional combustion products. So say you have combustion products here. Well, when your fluid goes out, it's going to be probably trying to go supersonic, and you're also going to be getting some expansion waves going back into here, which is going to help to suck this additional combustion product out of the cylinder. But what's important to note is that this is going to make a bit of a pop noise. If your engine is going at a few thousand RPM, then you're going to have more pops for every you're going to have more pops for every second that the engine is running, and as a result, you're going to hear a different sound. So that's an interesting point with regards to this pressure ratio. That's more what you're hearing. You're hearing the air exiting the cylinder, the air exiting into the muffler. You're not so much hearing actual combustion. That's not what's making the noise in the engine. If you have an older car, perhaps you're hearing some belts slipping as well, or perhaps you're hearing some other noises as your car breaks down slowly. But that's essentially what that noise is. So, I'm Spider Pilot 747. What we're going to talk about next time we're going to be doing a diesel cycle. And we're going to ask, is it more efficient? So, I'm Spider Pilot 747. Thank you for watching this. If you enjoyed the video, please feel free to leave a like. Subscribe if you want more, and feel free to ask any questions if you felt something was unclear. Thank you, and have a great day.